In this video, we are going to talk about how can we classify and graph polar equations. And we've already seen how to graph those in Desmos, but we're going to talk about classifying them and graphing them by hand. So let's start with some lines, and I'm going to start with a horizontal line. Horizontal line is always in the form of y equals b. So where b is some kind of constant. And remember, when we're thinking about making this a polar equation, we're going to think about all of the substitutions we could use. So we know y is equal to r sine of theta, x is equal to r cosine of theta, and we know x squared plus y squared is equal to r squared. And tangent of theta is equal to y over x. So those are the substitutions we could think about making. So for horizontal line, if we make a substitution for y, which is r sine of theta, we could write a horizontal line in polar this way. R sine of theta is equal to b. Likewise, for a vertical line, we're thinking about something that's in the form of x equals some number, a. Make a substitution for x, r cosine of theta. So then we have r cosine of theta is equal to a. Now, if you're graphing these on your calculator, a TI-83 or a TI-84, you do have to solve them from R and then put your calculator in polar mode. But if you're doing this in Desmos, you could type it in just like this. You don't have to solve for it. So if we talk about any other line, like y equals, think about the line y equals mx. So it's a line that goes through the origin, so that y-intercept is 0. If we want to think about graphing that line, we need a substitution for m. And we could think about substitution for m really in terms of this angle from the positive x-axis up to that line. And we could write that angle in terms of the tangent function. As long as we know a y and we know an x, then we know what that angle would be. So we could rewrite y equals mx as y equals tangent of alpha times x. Or tangent of alpha is going to be representative of our slope there. And then if we make our substitutions, r sine of theta is equal to tangent of alpha times r cosine of theta. And then now let's divide everything by r cosine of theta. So we're going to have tangent of theta on the left is equal to the tangent of alpha on the right. And if I take the inverse tangent of both sides, I'm going to get alpha on the right. So that's where this polar equation is coming from. So a line can be written in terms of theta is equal to alpha, as long as we know what that angle is to produce that function, that y equals function. Okay, circles. We've got x squared plus y squared is equal to a squared. That's a circle centered at 0, 0. If we were to make our substitutions here, we have r squared is equal to a squared. Take the square root of both sides, and we could think about it as r equals a. Now, if we transform that circle either to the left or to the right, okay, so we're just moving that point of that center point over to the right, or we could move it to the left, then we could rewrite this as r equals either positive or negative, depending on which way we move, 2a times cosine of theta. So notice that change here. Okay, cosine of theta because we're shifting left or right. But if we were to shift this up or down, notice it's going to have a sine of theta right here. So when we could play around with this, let's go to Desmos. So just to give you an example, let's say we have x squared plus y squared is equal to 4. That's going to be a circle centered at 0, 0 with a radius of 2. If we wanted to write that in polar, we would say r is equal to a. And you can see how that's the exact same function as that red one. So now let's shift it. Let's say we had x squared plus y squared is equal to 2 times a, which is the radius, times x. You can see how that shifted the graph to the right. And if this would have been a -2 in front, it shifts it to the left. And then polar form for that would be r equals 2 times our a times cosine of theta. And you can see how that purple graph is identical to that green graph. And then likewise, if we were to change this to a y, it's going to shift it up. And if I change this to a sine, it's going to shift it up as well. So once again, that green and that purple are on top of each other. All right, so let's go back to our notes. So, and we do have a few other equations I just want to kind of make you aware of. We have a cardioid. If we have something that's written in this format, it's going to create a cardioid, which is kind of like a heart shape. We do have something called a lemicon. Okay, here's the format for a lemicon. Sometimes they have a loop on the inside and sometimes they don't. It really depends on your A and B. If A is larger than B, we're not going to have a loop. If A is smaller than B, we will have that inner loop. And then we have some other figures. This kind of looks like a helicopter propeller. And then we have roses. All right, so what we're going to practice in this section is converting back and forth between rectangular and polar form. And then we're going to look at identifying some of these. And then we're going to look at some symmetry, and then we're going to graph one by hand. So let's look at just a few. Let's look at number 15. So in number 15, we have theta equals pi over 3. So if we were to compare with our little cheat sheet up here, we know that's going to be the equation of a line. And if we wanted to write that in rectangular, we can take the tangent of both sides. Tangent of theta is the same thing as y over x. The tangent of pi over 3 is square root of 3. And so that's going to be equivalent to y equals the square root of 3 times x. So you could see your slope here is going to be square root of 3. Let's look at another one. Let's look at number 24. So if we were to compare this to our formats up here, we see that's going to be a circle. It's going to have a radius of 2, and it's going to be shifted to the left because of that negative. So let's turn that into rectangular form. We have r equals -4 cosine of theta. I'm going to multiply by r squared. Make our substitutions. I'm going to move the x terms to the same side. And then we're going to complete the square on the x's. So I'm going to take half the middle and square it. Half of 4 is 2. 2 squared is 4. What I add to that side, I got to add to the other side. And then this guy's going to factor. And you can see this is a circle with a center at -2, 0, and radius of 2. And that's exactly what we said. This was going to be shifted to the left 2, and it was going to have a radius of 2. And we knew that because of the format. Let's look at number 39. So 39, if we were to compare, is going to be a cardioid. And the difference between the cardioids and the lemicons is cardioids have the same value here and here, so we just think about A, whereas the lemicons have two different values here. And if we wanted to write that in rectangular, we could multiply everything by R, make our substitutions, and this is just not going to be a very nice equation there. We know it's not a function, right, because it fails that vertical line test. And then let's do maybe one more. What about 54? So if we think about our formats here, 54 is this, lemniscate, and if we wanted to rewrite that, we could multiply everything by R. Actually, let's multiply everything by R squared. I think that's going to make things easier. So we're going to have x squared plus y squared times x squared plus y squared. And the reason I did that is so I can rewrite this. This is going to be 2 sine theta cosine theta. And I'm going to think about that right-hand side as r sine of theta, r cosine of theta. And then we know this is y, and we know this is x. Okay, so the reason I had to rewrite this sine of 2 theta is I don't have a substitution for sine of 2 theta, but I have a substitution for sine of theta. So there's my rectangular equation that would produce that.